ఆన్ చేసా చూడు. హలో. హలో. గుడ్ మార్నింగ్. మార్నింగ్ ఆల్. హలో. గుడ్ మార్నింగ్. హలో. గుడ్ మార్నింగ్ ఎవ్రీవన్. వినిపిస్- హలో. గుడ్ మార్నింగ్ ఎవ్రీవన్. హలో.
Hello.
Good morning, everyone. The session will be started within few minutes. Thank you. Thank you. Mhm.
Good morning, everyone. We are going to start the session very soon. Today is our speaker is Dr. Vishwanath Bunia from Department of Bioengineering, National Institute of Technology from Agartala. Sir is going to give on the topic secondary metabolites, process design and analysis. There is no delay, sir. We are going to start the session very soon.
Hello.
Sir, good morning, sir.
Hello.
Sir, good morning, sir.
Yes, good morning. Good morning.
Shall we start, sir?
Yes. You can start.
Yes.
A very warm welcome to the third day session of Frontiers in Life Sciences and Value-Added Products from Bioresources, conducted by Department of Biotechnology VFSTR in collaboration with ICAR. Now I would like to invite Sai Teja to introduce our today's speaker, Dr. Viswanath Punia, Department of Bioengineering, National Institute of Technology, Agartala, Tripura.
Honorable speaker, faculty, and participants, I am glad to introduce the profile of Dr. Vishnu Bunia. He is a distinguished academician and a research renowned for his contributions to the field of biotechnology. He earned his PhD in the biotechnology from National Institute of Technology, Durgapur, with accolades including the DST Fast Track Young Scientist Award and CSIR RA Fellowship. Dr. Bunia embarked on his academic journey in the Department of Engineering, the National Institute of Technology, Agartala, in 2013. His research endeavors focus on various aspects of secondary metabolite production utilizing organisms such as fungi, bacteria, cyanobacteria, and algae. Dr. Muni's expertise spans bioprocess engineering, environmental biotechnology, pharmaceutical biotechnology, and bioinformatics. A dedicated mentor, he has guided numerous students at different academic levels and served as visiting faculty at various esteemed institutions, including FLSVAPB, GM Vilakia College of Applied Sciences, Vapi, Gujarat, India, Department of Biotechnology, Mesra, and Department of Biotechnology and Bioinformatics at Northeastern Hill University, Shillong. Dr. Munya's contribution extend beyond academia as evidenced by his editorial roles in reputable journals such as Protein and Peptide Letters and Current Pharmaceutical Biotechnology. He has also served as a guest editor for journals like Current Alternative Energy and Recent Patents for Biotechnology. In addition to his editorial responsibilities, Dr. Bunia actively engages in reviewing book proposals from major publishing houses like Elsewhere and Springer. Furthermore, he played a significant role in the development of proposed syllabi for PG, that is Pharmaceutical Biotechnology, at South Gujarat University in 2007. With a prolific publication record comprising 79 peer-reviewed papers, one patent, 15 book chapters, and one book, Dr. Krishna Punya continues to make significant contributions to the advancement of bioprocess engineering, bioinformatics, enzyme and microbial technology, and advanced purification process and modeling through his research and scholarly endeavors. Sir, the forum is all yours.
Good morning. Am I audible? No? My sound is clear? Hello.
Yes, sir,
Okay.
you're audible.
Good morning to all of you. Thanks for your nice introduction, Sakira. I would like to thank organizer, faculty member of the department, Bignan Foundation for Science, Technology and Research, Andhra Pradesh. Specially thanks Dr. Bobby, Associate Professor. Head of the department, Program Director, Dr. Wen Thierry, Principal Scientist, IARI, New Delhi, for giving me an opportunity to share my thoughts for 6th-day FDP program on Frontiers in Life Science and Value-Added Products from Bioresource from 12th to 17th Feb 2024. I welcome all the participants, researchers, faculty members, scientists for this session. Today I will discuss on the topic process designs and analysis of secondary metabolites. Although most of the part of this topic will be in the designing of the process, including reactor designs and analysis, how we can design a reactor for the secondary metabolites that little bit be different from the primary metabolites also. Here, major portions will be on the mathematicals as well as engineering point of view, how we can make or scale up the process. Everybody know what is secondary metabolites. Secondary metabolites that usually are produced in the late phase of the growth phase, normally in the stationary phase, and it's a very low molecular mass products. And normally it is not directly involved in the growth, but it has a significant role when we think about the defense point of view. Although secondary metabolites are very important for health, nutrition, as well as economic of our society, because the most of the if you see that most of the secondary metabolites that are these are very biologically active, such if you think about the antibiotics, pigments, enzymes, these are the secondary, these are under the secondary metabolites. They're having some biological activity. But when we are going to design a process, our motto should be that cost of this product should be very less when we are designing process, because most of the designs are two centric. One is the fermentations where the reaction process is going on. Another is downstream process. So downstream process around 40 to 60% of the total cost they contribute. Here I have given some examples of the biomolecules and their cost in US dollar. If you see, when you are considering the cost of the secondary metabolites, there are two parts. One is the fermentation and reaction part. Another is the downstream part. Those two are separately and individually standalones. One is the downstream part. There is no chemical or no biochemical reaction. It is a very physical process, and then it is a separation process. Mainly unit operations. What we know that unit operations are starting from your filtration to centrifugations, then that chromatographies, all the liquid extractions, all of the things, all are included here. But when you design it out,
Hello, sir.
Voice is not audible.
Sir, your voice is not audible.
Okay. When video is still speaking now, it's still talking. So, his net is
Sorry for the technical issue. The session will be started in 3 minutes.
Hello, I'm extremely sorry because due to some problem, I don't know what happened. Hello?
Yes, yes, sir.
So I'm not unable to share, madam. Host disable participant screen
Yes,
sharing.
yes.
One second.
1 second, 1 second.
Yes, yes.
Yeah, you are the host now.
Yes, yes. Madam, I don't know what happened, but anyway.
Participants, sorry for the inconvenience.
Okay, okay. So in our previous discussion, in a previous just interruption, so what we have discussed that there are two different aspects. One is downstream processing, another is the biochemical reaction. So downstream processing I already discussed. It is a totally that unit operation is not related with any biochemical reaction. But bioreactor operation, that is very important when you are designing any secondary metabolites. So here you need to think several things, not only how you are going to design a reactor, how you are going to design a process, but you have to think about how you can improve a strain, or how can you optimize the media. So as a whole, you have to think about the process. So process is not the simple the batch process, fed batch process, or what you are adding is not like that. It is as a whole, and the concern of the reactor design to starting to the reaction strain improvement and to the reactor designs, it will be that bioreactor operation. So everybody might know that various kinds of bioreactors are there, and bioreactors usually that operated in a different mode. But the usual reactors which is used is the stir tank reactor, that is a batch reactor, and batch reactor operates under the batch conditions and is under the unsteady state conditions. So unsteady state conditions means there will be no input and no output. Once the operation you have started, if you think about the productions of any secondary metabolites, or any biomolecules, the primary metabolites, your reactor, either it will be the operated in the batch mode, or it can be operated in the flow mode. There are two kinds of operation process. But when you are designing a reactor, there are two things you should keep in your mind. One is it should mass should be uniformly distributed throughout the system. So that is the main constant, and normally not happens in the reactors, ideal reactors, in the real reactors. But ideal reactor, basically it should be, when you are designing a reactor, then we assume that our reactor is the ideal reactor, and there will be no heterogeneity in the mass distribution, mass transfer, heat transfer, or any other concerns are assumed. That we'll think that uniformly all parameters are distributed. Practically it is not happens, whatever it may be. So we need to think what we are required for the biochemical reactions, and why we are talking about this as a reactor, because reactor means here your reactions will take place. That might be the biochemical reaction. That's why it is called the biochemical reactor. And the catalyst, either you have to use either cells, or that may be the animal cells, plant cells, or microbial cells. But the catalyst, either it will be enzymes. So biochemical reactions are very limited in the regions. What is either cells or the enzymes will be attached for this. But chemical reaction, that is a little bit different, and their considerations are totally different, and they are not considered about the that parameters requirement, because we know we are dealing with the living system, so temperature, pH, that need to be adjusted. But in the chemical reactions here, it is not such requirement, because chemical reactions happens at the higher temperature, and you know that most of the cases the reactions the reactions, once reactions happens, that rate constant value, basically elementary rate, like you see, the rate constant value increase with the temperature. The Arrhenius law indicates that if you increase the temperature, your rate of reactions will be increased. So that's why chemical engineer people, they believe that reactions should be at a higher temperature, and it will be good for output. But biochemical reaction, there is a constant. Here your cell will die, so you cannot go beyond that. That's why you have to do several control systems. But we are not going to details in the control system, but how we can manage this controls part in the reactor, that is also should know that when you are designing a process. Basically, a reactor is the vessels, and where that height and diameters, there should be some aspect ratio, and that is not fixed. Even for reactor species to species, it will be changed. If your species what you are using for productions of secondary metabolites that needs more oxygens, so definitely your height should be very high, and the residence times requirement should be residence time, yeah, residence time requirement should be definitely residence time requirement should be very high. So that need to be taken care. But usually hum rule is h by d, that height by diameter is keeping in the one in the range of 1. Now, another important part is that since the process are always the most of the biochemical process are the aerobic process, so you need to taking care that how you are giving the air in the systems, because the air you are giving from outsides, and air that need to be properly sterilized, and filter is required for that. And what will be the surface area of the bubbles, that is also very important, because that will help for the mass transfer. So spudger that is there, you can see this is a spudger part, and here that area is completely spuds, and that is the inlet. And temperature control usually done by the two part. One is the heater is there, that will completely, if the temperature is less than the optimum temperature, then you have to automatically your heater will be on. And your the cooling systems, that is also important when you are going to design. That is also basically based on the that mathematical expressions. And baffles, that is a work baffles basically that remove the vortexing of the system mixing when the impeller is moving inside the systems. A vortex may generate, and that vortex basically indicates your reactors is not uniformly mixed. I told when I discussed the design part, then I told that your reactor should be a reactor should be uniformly that mass and heat should be properly distributed. But if the vortex forms, that cannot be. That's why baffles is usually used. And these are the impellers. There are three parts. So first impeller, second impeller. It is also sometimes called the foam breakers, because most of the media contains compounds that is basically the proteinous in nature. So if you that rotation happens inside the reactor, then frothing can generate, and that basically is not expected. And that's why that anti-foaming probe will be there. Once probe will be touched, the froth will touch on the probes, then automatically you have to add the silicone oil or the foam breaker you have to use to break the foam. And other that basic things, these are the temperature and pH required. One pH probe is there, that also maintaining the how much pH is required. Although such type of requirements not so much required for the chemical reactors, but biochemical reactor is mandatory and should be properly sterilized conditions. So this is one beautiful examples that picture I have shown you, that is the for the state tank batch reactor. Now, if you think that your design process require oxygen, much oxygen, but that your strain are not able to tolerate the damage due to the impellers. So there can be some problems. That means you need more retentions of the bubbles inside the systems. That means your length should be, height should be of the reactor should be very high, because bubbles have sparks in the bottoms and it will slowly move to top. So that means your residence times of the bubbles, if you want to increase, then height of the reactor should be high. So height should be more than the diameters. That is the first. Second one, some cells, basically animal cells, they cannot tolerate the impeller what you are using, because huge damage happens. So basically, that case you can avoid this impeller. But in the same times, you need the mixing also. That's why you can think that there is a very poor mixing, but mixing can be possible. So what is required for the animal cells? But here is the problem. Problem is that when the you are sparging the air, so in the bottoms, the density of this liquid will be low and the upper density will be high. So definitely low density liquid will go to the up and high density liquid will come to the down. So there is a chaosness. Now there is a local mixing will take place. There is no uniform mixing. For that, this is called the bubble column reactor. Then we can slightly different the designs of the bubble column reactor in the air-lift reactor. So here the configuration is totally different. You just see there is a input that input here is this region only. So liquid will be low dense liquid will be go up and high dense liquid will go down. So there is a two enter presses that design also you can do for the animal cell cultures. Here the advantage, first advantage is the maximum cost the electricity you have set because your impeller is not there. If impeller is required, say every time if your impeller is moved, then you need some cost that you have to sponsor. But here your cost will be minimized, but you have to compromise with the mixing because in the stir tank reactor where the impeller is there, their mixing will be very proper, but here mixing will not be so much. Now we can discuss the another kind of reactor, that is the packed bed reactor. So packed bed reactor is basically used for long time uses. Stir tank reactor, what you can do after completing your experiment, you have to throw all the things. But packed bed reactor, you can use the bits repeated times so that you can minimize the cost also. But this is a heterogeneous reactions happens, it is not homogeneous reaction. Heterogeneous reactions happen means that mass need to be transferred from the media to the inside the catalyst. So that is very mass transfer limitation problems will come. So that's design criteria is a little bit different from the previous reactors what we have discussed. Now here you understand that the two phases happens. One is the solid phase where your catalysts are interrupted. That catalyst may be the cells or enzymes, and your media is the liquid phase. That are two different phases, so there is a concentration gradients happens, and that concentration gradients basically limit the mass transfer. And if your catalyst is very strong but your mass transfer is not properly happening, then your interproduct formation will be very less. So this is one that step I have taken for the fluidized bed reactor, that is packed bed reactor. And if you see, this is a one difference between the packed bed and fluidized bed. What you have see here, the beds are very packed. So surface area, the effective surface area of the catalyst, that will be very less. But here you will see that all bits behave like a fluids, not is a solids, because they are just moving in the reactors. So an effective surface area will be very high. So if you want to design such type of things also, that can be. But here is the limitation is your reproducibility, not reproducibility, that age of these beads will be very less, because once they will move like a fluids, they can attract each others and they can degrade. So you can use 2 to 3 times, not more than that. But packed bed you can use repeatedly 4 to 5 times. Or here is the longevity of this beads. If you think about that, fluidized bed is less and packed bed is more. But fluidized bed, the effective productions of the any molecules through the fluidized bed, that definitely will be more than the packed bed. Another reactors I have not shown you here, that is the plug flow reactors. That is normally not used for the biochemical reactions, only for the continuous sterilization process that is used in industry, that is plug flow reactors. And that also is a little bit I'll touch when the design considerations will come. Next, we are going to design as a whole that process indicating the reactor designs as well as the that reaction engineering considerations when you are going to design any secondary metabolites. Let us very short discussion on the batch cultivations, because already we have discussed on the batch cultivation process, what we have to do, because there has been no input, no output once the reaction is started. But here the main problem is that your mixing that need to be effective, should be effective. But thing is that what you think and should not be normally not happens. That due to the how good you have skill to design a impellers, that impeller will tell you how effective it can be help for mixing inside your reactors. Now, if you think there are different kind of impellers are there, and their flowing the moving process is different. That there are various kind of impellers are there, and that impellers can be designs based on your requirements, what you need. This is one rotational part. Then if you see, that is a circular motions of the that rotors happens. That basically looks like a fan. If you put a one fan inside this reactor, so your liquid will rotational movement of the fluids happen inside the reactor, but it is not the uniform mixing of the reactors inside the systems. So that basically creates a that vortexing inside the reactors. That means if you think about that a reactor, you have designs where your impellers are there, but your vortexing happens due to the rotational mixing of the impellers rotation. So that is not desired when you are designing a reactors. So that's why you have to use the baffles. So what I have told in the before the 2 to 3 slides, that I told that the utility of the baffles. Baffles basically help to remove this vortexing, and it is a regular phenomenon. So what if you do in the small scale, that problem you may not face. But in the large scale, when you are going to design in the large scale, in that case, you have to take care, because that might disturb your that overall process. So in that concern, if you think, then you need to think for the baffles too. Now, another flow patterns of the impellers, if you see, this is a radial motions of the fluids. How it is happens, your impeller, when it moves, then that liquid are flowing in the both directions. One is the left direction and the right directions, but it's 90-degree angle with the your impeller shaft. So this is a 90-degree angle. It is the liquid is moving. But the thing is that once it touches to the walls, basically that is divided in the 2 directions. Now that is the 2 directions, and one directions is going to up, and it helps to mixing in the upper regions, and second portion in the lower regions of these impellers. And there are 2 kinds. So there are 2 things happen. So this part is called the impeller clearance. So impeller can able to mix in that region, that is called the clearance of the impeller. Now how many numbers of impeller you need, that depends on how many heights of your reactor is. Usually thumb rule is that 1/3 diameters of the impellers, that is the total diameter of the tank diameter. 1/3 of the tank diameter is the impeller diameter, and clearance is the 1/3 height of the reactors. But it depends. It is not the thumb. It may change. It depends on the requirement what you have. If your species needs more oxygens, then your requirement will be again changed, because you have to think about residence times, not only the mixing. So everywhere you have to compromise. Now, another part is the axial type of impeller. So here you see that is the previous impeller. And here the another type of flow regime where the impellers rotate, but liquid pumping efficiency here is a different. Direction is different. You can see the axial direction here is not 90-degree of the impeller shaft. So here the mixing as a whole, if you think that happens in the axial direction, but always that is ideal condition what we are looking is not practically happens. That's why sometimes dead volume is there, that basically affect when you are not whatever you were expecting is not happening due to the dead volumes. If your dead volume is very high, your impeller clearance is not good, then your product will not be as far. Now, you can see there are various kind of impellers are there, but how will I choose a impeller and which impeller is good and which is bad? But there is no thumb rule that this is good, this is bad, but you have to think on your requirements, what you need basically, what is your requirements. This is the first one is the 6-plate disc turbine. That is most of the reactor you will see that is used for the microbial fermentation process. And if you are looking for the secondary metabolites from the microbes, then definitely that impeller you will see in the reactor. But the problem is when this reactor, this turbine is moves, looks like in the rotation, particularly directions. Once bacteria will hit these walls, that basically damage of the cells happens. You cannot say that damage will not happen. So we need to think about and coming later. And this is propeller. This is basically rotational motions and pitch blade turbines. And this is anchored and depends on your viscosity of the media. You have to choose your impellers. Here I have shown you some that impeller type and viscosity. So if you think that your viscosity is 10 to the 4 range, then you can use the propellers or flatbed turbine. So most of the cases in our that microbial fermentation process, some fungal fermentation, it's quite a little bit problems, but up to the 10 to the 4 range, our fermentations broth viscosities looks like. So that's why we always prefer to use the turbine types. Turbine type flatbed turbines or Ruston type turbines that is used in the reactors. So these are the scale, how what will be the viscosity of your systems and how you can use which kind of impeller. Now there are two different design I have shown you. One is that 6-blade turbine, flat turbines, and another is the Ruston type turbine. You can see the designing of the two different impellers. And if you think that why should I use the Ruston and why turbine, because both are same type of radial flow impellers. They are helping to mix, but why should I Ruston? Because your electrical cost is very high than the turbines. That is an important thing here. Just see the designs. Once your bed is flat, when it moves, then basically your bacteria hit the walls, it damages. But if it's curvature, then basically bacteria will not hit, it basically kiss the walls. That basically there is a less damage. So if you think your bacteria is so sensitive, then you have to think about the Ruston type turbine. So everywhere you can change your design, and that is the beauty of the engineering science. So what is your requirement, and accordingly you can shift your designs. So Ruston type turbines, there should be some advantage already told, but the cost is very high. What is the cost? Basically, the electrical requirements for particular RPM. Now, another problem if you even choose the right impeller, but what will be the relation between the impeller speed as well as your the air flow rate, because that too is very important, and you have to correlate when you are going to design any production process. Let your impeller is there are three conditions basically happens. Sometimes you will see that you are giving the RPM, but your impeller is not moving, because that is called the flooding conditions, because your impeller is not moved, because your air bubbles are blanketed your impellers, so that your impeller, even it is on, it cannot move. This is called the flooding regions. Now, if you slowly increase the impeller speed, then what happened? It will start to move. That is called the loading regions. If you increase more than that, then your it's called the continuous mixing process. So you have to think about how much oxygen is required, how much flow rate you have to decide it, what will be the retention time, and what will be the RPM. So as a whole, if you think about, first case is the flooding case, where your impeller is totally interrupted by the blanketed by the air bubbles, and here your air bubbles are slowly thrown by the impellers, and here is the complete mixing of the impeller takes place, and that you have to also taken care when you are designing reactors or process. Now you can see that is reactors. What you need, 100 RPM is enough. 100 RPM is not good. You can see is the blanketed, total blanket air bubbles blanketed these impellers. 200 also is there, but 300 is very less, and 400 you cannot. So that part also you have taken care when you are designing any process. Now, this is one that gas cavities happens. So your impeller is not moving. It's happened normally the pump, and you may know that it's called the cavitation process. Your pump is totally blanketed by the ears, so that's time you have to give the waters. And here also same thing. Your impeller is also pump. It also when it is blanketed by the air bubbles, because in your system is the aeration process, so you need the oxygen, we need the air. Without air your cell cannot survive, so you have to give the airs, but there is a limitation again. So how much RPM you have to fix, that also need to be taken care. So design means as a whole, you have to think everything. Not only you are giving the something in the media and your product will come, and why it is not coming in the large scale, that need to be also taken care is the prime part of the design. Now, how do you check that you have designed everything, but how do you check that your reactor is actually ideal reactors or not, or properly mixing happens or not, or how long time is required for the proper mixing? That also you have to test once you have started. Before that you have given one that dye you have can give in the reactors, and you have to check how long time is required for the uniform concentration throughout the reactors. That also you can that is the one picture I've taken from the books. That is the how the trace concentration is changing within the reactor. And if it takes a long time, that means your mixing time is required more times. So your impeller is not properly designed, your baffles is not properly designed, your reactor is not properly designed. Even you optimize the media, even you have selected a good strength, your output will be very less. Now, another part, we always forget that we never concentrate on the fluids behavior, because reactions only happens if you have substrate, but your substrate will be taken care by the fluids. Fluid is the carrier, will bring your substrate from one place to another. So we never discuss the fluids behavior. So you have to know the fluids behavior first, and this is very important. That can be understood by the Reynolds number. But Reynolds number, that when liquid is moving through a pipe, when liquid is moving inside the inside the reactors, both behavior are not same. So when liquid is moving inside the reactors, that is called the impeller Reynolds number, because impeller will help to move the liquids, and that Reynolds number definitions is different than the when liquid is passing through a pipe. That is completely different. So here the turbulence range will be around the 10 to the 4. So here you can see that is the that Ni is the tip speed, that basically RPM, that which RPM you are moving your impellers, and the TM is the mixing times. You will see that at the turbulence regions, your NITM, product of the NITMs are the constant. So that basically is very important, because if you increase the Reynolds number, you will see your the NI product of the NI and TM will be reduced drastically up to the laminar regions. But turbulent regions, it is exactly same. So you have to think which region you need, where your viscosity is, what is the media. So is it bacterial fermentation or fungal fermentations or algal fermentation? So accordingly, you have to scale where you will be your TM value, what will be your the RPM value. So variation of mixing times that I have shown, that is important when you are going to designs. Now, sometimes I already discussed that the clearance of the impeller is very important. You cannot give one impellers for mixing of the throughout the reactor. It's not possible. So that is a clearance. Clearance is the 1/3 of the total height of the reactors. So if your height is normally, but it's not exactly equal for the all impellers. Basically, we are talking about the Ruston type turbines, which is normally used for bacterial fermentations or fungal fermentations. So that is 1/3 of the height of the clearance of the impellers. Now, if you see another beauty of these pictures, if you see there are multiple impellers, you will see that mixing times requirements in the bottom regions. So you will just see that is that region your mixing time will be less. But in the wall side, your mixing time will be very high, because wall side will get the more more hindrance due to the viscosity. But central, your force is very high, that can remove the viscosity. So the time requirement is very less. So you have to think properly that what will be the exact RPM required, so that uniformly mixing can take place. Without mixing, it cannot be that your reactor is not properly designed. Now, that is one example I basically would like to share, because the animal cells, when you are cultured in the microcarrier systems. So here your animal cells are interrupted. Till now, whatever we have discussed about the microbial cells, but animal cells are very, very sophisticated, and they are not so much robust. That they cannot tolerate like bacterial conditions. So sometimes whatever the impeller you are using, that may sometimes create the hindrance and can damage of the cells, and that cannot be tolerated by the animal cells, which might be in the for the microbial cells. And then either you have to remove the impellers. So once if you remove the impellers, or that impeller, if you remove, then it's okay, but there will be oxygen requirement will be very less, and mixing will not be proper. So if you even start the mixing, then you have to think what will be the RPM. So if you remove the your design is not proper, then there is a chance of the ADs will form. So ADs means basically the that turbulence of the fluids inside the reactors. So if your animal cells, if your carrier size is small and at this diameter is big, then little bit it is safe, because your cell will, your microcarrier will move within the this. There will be less damage of the animal cells. But if your AD size is very less, but then the microcarrier, then it is a huge damage will take place, because your microcarrier will move like looks like. So all directions your that carrier will get the force, and that basically help to damage the animal cells. So that also you need to take in care of what will be the RPM and what type of impeller you have to use. Here, this should be minimized. Either your cell will damage, maximum cell damage takes place. Another things, basically, it happens on the aerobic fermentations takes place. That is also another key features that also you have to take in care, because you are sparging with the ears at the bottoms, and that air bubbles will go up, and once it go up, it will burst. So you just see that is one liquid jet will form. It is not the problem for the microbial fermentation or fungal fermentation or algal fermentation. It is a problem for the animal cell cultivations. If animal or plant cells, if such type of jet forms, then you have to minimize, reduce the surface tension immediately by the surface tension reducing agents. Some oils you have to use. Either it will once the jet will form, that will destroy your cells. So that need to be also taken care when you are designing a particular secondary metabolite production from various cells, or microbial cell, animal cell, plant cell, anywhere. Now, after all, whatever you did, if it is well run, and that your mixing part is totally, you have minimized the error due to the mixing, that's fine. Then you have to think about the mass transfer problems. So what is the mass transfer problem here? The years, you know that most of the people know that the oxygen is spanning the solubles. So spanning the solubles means around 6 to 8 milligram per liter of oxygen can be dissolved in the waters. And if your cell requirement is very high, then how that oxygen can be transferred from the air bubbles to the liquid to bacteria, or air bubbles to liquid to fungi. So there are three different phases are here. Bubbles is the gas phase, and the liquid is the water is the liquid phase, and your bacteria or fungi the solid phase. So there is a problem. So there are everywhere your boundary layers, everywhere your resistance, everybody must be taken care here, because the heterogeneous reactions means you are always that output will be less. So heterogeneous systems you are using, heterogeneous system means your mass will be transferred from the from the air bubbles to the liquids, so your concentration will be reduced. That means if initially it is, you are assuming that 6 to 8 milligram per liter oxygen is there, once it will come to the water, it will be reduced. Then water to, when bacteria will go, it will again the liquid solid mass transfer ratio. So then it will be reduced. If your oxygen requirement is very high, then it may not be the air sparging is sufficient. Then you have to additional oxygens. So that need to be supplied, because that really create the catastrophe of the cells. You will know that everything you have given, but your cell is not, your product is not formed. Most of the cases in the fungal fermentation, this problem arises, because fungal fermentations is very difficult to handle. Whatever I handle in my careers, although that bacteria, fungi, algae, all we have handles, but fungi handle to fungi is very difficult, because fungi has several phases. That initially they are in the germination tube, high P, then mycelium. Once mycelium in the higher forms, that they will create the problems. They will not produce any product in that condition. You have to give the shock either for secondary metabolite productions. That we'll discuss if time permits. We'll discuss in the next page. So we have to take in care that volumetric oxygen transfer rate. That is the one indicators when you design a reactors. Your reactor is really sufficient to supply the oxygen or not, or agitation and aeration, that both capacity is sufficient or not. That can be understood by the KLA value. That is called the volumetric mass transfer coefficient. So here volumetric. So here is not the mass transfer coefficient, is the volumetric mass transfer coefficient. That means your boundary layer, that is basically the area that you cannot never measure, because that the boundary layer area you never measure, because it is always increase or decrease depend on the mixing efficiency of the systems. So that's why that mass transfer rate along with the product of the that area, that area required for. So if that is called the volumetric mass transfer rate, its unit is time inverse, and that is the indication for the if your KLA value is very high in the systems, then you can say, okay, that is good for high oxygen requirements. If in any reactor requires, that KLA values need to be checked before that. If your KLA value is high, then oxygen requirement, if any microorganism needs higher oxygens, then that system is okay. So here there is some expression, and that how can you calculate, that is given, but it's not important so much. Now I'm just going to discuss about the mathematical expressions. How can it design? Basically, the design means what? If you are talking about the mass transfer, if you minimize all the things, then the design means in the reaction engineering perspective, in the batch reactor is the time, how long time it requires for particular products. Basically, that is the engineering language, that how long times required for getting the certain amount of products. Here is the very clean systems. There will be that input minus output plus generation is the accumulations. So in your reactors, if you think that is a batch reactor, or it is a flow reactor, whatever may be, so there is a very common equation, that is the input minus output plus generation is equal to accumulation. So already I told that there is a batch reactor, there is no input, no output. So it will be the zero, but generation is there. If your product is formed from the substrate, so definitely it is a generation. If you are calculating the products, then definitely it's a positive generation. If you are calculating the substrate, then it is the negative generation, because your substrate is not basically generated. It is basically consumed, and bacteria is consumed your substrate, and your product is formed. So that is the consideration. So how assumption you are taking during the calculation, that is very important. But after all, design of the batch reactor means you are only finding the time for completion of the process to achieve certain amount of products. So what you are expecting or calculating from the systems. So if you think that that amount can be produced, so you cannot go beyond that. Now that batch reactors, basically I told that times, that is important, and in NA0 is the initial concentrations of your substrate, and NA is the final concentration of your substrate. So that is simply derivations and mathematical compulsion is here. So you have to design. If you design means some mathematical part that also should be taken care when you are designing. Basically, what happened, your substrate is going to reduce. So substrate is reducing with times, because there is no input, no output in the batch process. Whatever you do the work in the conical flux, so that is also batch reactor. But here also, once you have started your experiments, you cannot stop it. Once you stop, that means your process is over. So that is one kind of batch reactor. Now another is a fed batch process. So basically, for secondary metabolites production, fed batch process is very important, because you may know that when the penicillin comes to market, penicillin G, that times people had tried a lot in the batch process, but it is basically from the fungi, and I already mentioned the fungi handling is very difficult. And that fungi, if you give the food, fungi will consume it and it will grow fast. And then at the stationary phase, when it will basically shortage of the substrate, then it will start to produce some antibiotics, basically penicillin, but it's not sufficient. What you were expecting or not getting. Then people think that why we cannot give the always threat to the bacteria or fungi so that continuously they will produce the secondary metabolites. That is the beauty of the fed-based process. Here we are not giving the all food at the initial level. We are giving the food at the certain times interval so that bacteria or microorganism always feel threat that our shortage of foods. So here is the another problem is also there, because you will see that initial volume of the liquid, and after that your volume of the liquid will be changed. So but concentration never change. That is also another beauty. So that's why that volume will be always changed, volume will increase, but your concentration will not be changed. That is the main thing of the fed-based process, and that's why it is neither batch process, neither continuous flow process. It is a quasi steady state process. So only this thing will be taken care of when you are fed-based, you are designing a fed-based process. But here you should keep in your mind that the dilution, when the volume is increasing, that means dilution is happening. Here your specific growth rate of the bacteria, that should be equal to your that dilution of your systems, that is F by V. Now another part is the continuous step tank reactor. When you're going to design, I'm just going to touch a single reactor, because reactor might be in the queue. So in that case, the designing constants is there and designing criteria is there. We are not going to discuss on the details on that. But here only the continuous flow starting reactor. If you think that is, there will be always the input and always output, and you know that continuous starting reactor basically operate at the lower concentration of the substrate. So if you think that you will give the high concentration, then go for the batch process. So as per your requirement and convenience, you can use the reactors. But here it works under steady state, because always you are giving input and always you are getting output. So definitely always the concentrations of the reactant is remain the same inside the reactor, and that is the beauty of the flow reactors. But batch reactor, your concentration will always reduce. That means your rate of reactions is always reduced. So what about the rate of reactions at the beginning in the batch process? That will slowly reduce, and basically that will follow the monod kinetics. So monod kinetics, that for the growth of bacteria, you know that monod kinetics is very famous, but it depends on the substrate concentration initially, but after that it will not dependent, because if your substrate is concentration is very high. But continuous flow reactor is the beauty is here is the rate of reactions, or that mu specific growth rate that will always remain constant, and that should be equal to D. But one problem is here, if you somehow do not calculate the mu and the specific growth rate of the systems, you don't know, and you are increasing your dilution, then what will happen? There will be no bacteria inside the system. You know that bacteria is there, but exactly bacteria is not there. It's a completely wash out process. So it is a failure of the designing of the continuous flow starting reactors. So here we are giving the just examples in that up to that regions you have to wait, because if you suddenly go beyond that, your dilution is suddenly increased, then what will happen to your microorganism, the substrate will microorganism will suddenly disappear from the systems. It is called the washout DP. You should be taken care of that system. Here the mu should not be that dilution should not be greater than the mu. It should be always equal. Then you will get the yield. So that's of the beauty of the continuous flow starting reactor. So another part is the plug flow reactor. What I have told in the plug flow reactor, this is not basically used for the biochemical systems, mainly for the sterilization process we used. But it is not so much important for the biochemical systems used for the chemical systems. The only beauty is that in the radial directions, your concentrations, it will maintain the steadiness, and it should operate under plug flow. Fluid velocity should be in the plug flow region, so that you understand that Reynolds number is the fluid when its liquid passes through a pipe, when passes through a reactors, then your Reynolds number should play major roles here. If the fluid velocity is very less, then that will not behave as a plug flow reactor. So that also need to be taken care on when you are designing a plug flow reactor, but it's not so much important. Only in the sterilization process it is used. Now, another is the packed bed reactors that most of the cases we use the packed bed reactor, and it is used in the biochemical field because we interrupted our catalyst inside the beads, and some cases the when we need the continuous product. In the batch process, you will not the continuous product, but in the packed bed, you will get the continuous product. But the disadvantage is here, it works under the heterogeneous systems. That means there are two different phases is there. Solid bit is there. That means here the problem is the another problems that is not related with the batch process. Batch process. So batch reactor, what are the problems is that is not problem in the packed bed reactor, but the packed bed reactor problem is different. Batch reactor problem is different. Batch reactor problem is the substrate concentration is reduced, and the packed bed reactor problem is that mass transfer limitation is there. So advantage definitely packed bed has if your catalyst is very costly, your enzyme is very costly, so you cannot spend after one use, you can throw it. So you have to immobilize within the systems and then placed into the systems, and you go for the conversions or any particular biochemical reaction. So packed bed reactor is definitely good systems. So here the designing is a little bit different. The flow reactor, our intention is we have to find out the volume, but packed bed reactor, our intention is we have to find out the weight of the catalyst. So that should be taken care when you are basically designing a packed bed reactors. Here is the volume is not in materials. Here the weight of catalyst is materials that need to be taken care. Now, always I told that once you have designing confirmation is done, so you are supposed to move to the systems. Then you have to take care of the analytical parts. Actually, whatever you are expecting, that is basically happening or not. So that also we need to. Hello, am I audible? No, still.
Yes, sir, you're audible.
Okay. So the topics I have decided the design and analysis. So analysis part is also important because without the analysis, you cannot say that your design is perfect and your whatever that you have designed is perfectly done. So I told sometimes I'm getting some disturbance. Might be.
Yes, sir.
Hello.
Participants, please don't talk.
So that is the monod model that what I have discussed sometimes before. You will know that that is a Michaelis-Menten equation is for the enzyme kinetics that you have used, and monod model that is used for the cell growth kinetics. Michaelis-Menten equations, if you see that the V is equal to V max S by K plus S, and that you have plotted that V versus S plot, and here that plot is mu versus S plot. So a same equation, same type of equation, but only different is there V is the rate of reactions. Here the mu is the not rate of reaction, mu is the rate constants. That is the different. And basic elementary rate law when you are designing or going to analyze the system, then definitely the rate constant never depends on the substrate concentration, and it is written boldly in the books of any biochemical reaction books, either Fogler or any good books you follow. But in the biochemical reactions, it changes. It's mu is the that is rate constant. It changes with the substrate concentration initially. But here, why it is going to happen? Why it is not for the enzyme kinetics it is followed, but why the cell growth kinetics it is not followed? Because you know that cells basically enzyme kinetics, enzyme is a pure biocatalyst. That means they will not participate into the reactions. But in cell growth kinetics, basically cells take the substrate and product is the cells. So ultimate cell is going to increase. So number of multiplications of this catalyst is going to happen so in the systems. So that's why initially it basically rate constant is dependable if you calculate. Then once you calculate this calculation is done, then you will understand that why this specific growth rate or rate constant depend on the substrate concentration initially. After that, it does not depends. So that need to be taken care. Your system should be in the regions where it should not be dependent. That's why your substrate concentration, when you are designing in the fed batch process or continuous flows, your substrate should be in that region always, so that you will get the maximum substrate specific growth rate. So here one example I have given that you can understand that your system mu max is 0.075, case value is 5.7. So if your case value is very low, that means your bacteria love this substrate. So you can optimize your systems based on that what substrate should I use based on your specific growth rate. Also, this is also one evaluationary tools that you can use, because simple you cannot use any media for the productions of secondary metabolites. You have to choose the media which one is the perfect. Nowadays people are using various alteration methods. Some substrate they are scanning, and they can change that where your product is moved, but it's the small scale it might be. But in the large scale when you are doing, you need to take in care always in the technical terms, not in the simple doing the experiments and got the some data. Here you have to take in care that case value is very important, and when you are choosing any particular substrate for particular reactions. Now, if it is not properly fitted with the Monod models, because Monod gave this equation quite before, but nowadays people are using several models. If your substrate is a little bit inhibitory at a higher concentration, because some osmotic environment can be also some cases problem for the bacterial growth in the systems. So here there are lots of kinetic models out there, and you have to fit it your model, and you have to change what kind of model where it is fitted properly, and then you take this rate constant value for the designing of the reactors. So this is one example. So we have shown that how these models are properly fitted, and that both two models, IVA and DUS, are approximately fitted well with the data of the one of our students' experiments. Now, that is part of the growth part of the growth kinetics of the cells. But if you go for the substrate utilization kinetics, that means at which rate your substrate is consumed and where it is invested, your substrate, that also you need to take in care, because simply you are giving the substrate and your product is, if it is directly from substrate to product, so if it happens, then there is another kinetics. And if your product is the secondary metabolist, that means your substrate is taking as a food for their growth and the product will form. So that is secondary metabolist. Then that second terms will not be come into picture, that here the that second part, first part is the your growth associated. So your that substrate is investing for the growth, and here is substrate is investing for product. If your secondary metabolites, your substrate is not invested for the product, and the M stands for the maintenance. So some cells, when damage happens, so maintenance is required. So as a whole, whatever substrate you have invested, if it is not, if it is a secondary metabolite, the only the second term will be removed. So that only your substrate is consumed due to the bacterial growth and maintenance purpose. Now, another important part that is very important when you are designing, it is a primary metabolites or secondary metabolites. How do you distinguish that where it is produced? Only that basis, if you do, sometimes you may face problems when you're designing a process. Why I'm telling? Because 2000 Ludeking and period 1 model they have established. They told that any products, if it is even primary or secondary, or even it is a complex in nature, it is not distinguished properly. You have to calculate, analyze your systems, and you plot between the specific growth rate and specific production rate. Then you will understand what it is. So you just see this is the equations that nu is equal to specific production rate is equal to alpha into specific growth rate plus beta. Here the thing is that if you plot, if you get there are three kinds of things you can get. If your beta value is the 0, then it is a growth associated, it is a primary metabolites. If your alpha value is 0, then you can say it is a secondary metabolites. But if your alpha and beta both values are not zero, then there is a complex things that is not that it is happens in the mixed growth associated products. So either it is in the primary looks like some behaviors looks like primary metal. Even in the log phase also it can be generated, it can be produced. So that also need to be taken care of when you are going to design any secondary metabolites or any products in the process. So this is the things you have to calculate it here. What is the value of alpha and beta? Simply you're plotting and you will get the data. Now, one I told already that I will discuss on the secondary metabolites for the fungal systems, because secondary metabolites here is the enzymes is the xylanase. One of my students he did PhD on that, and that part we have going to discuss here. Here the fungi is basically there are spore phase to germination tubes they will form, and then if you give the proper median temperatures, then they will go to the hypophones, then mycelium, then they will give the product. So this is the one things I'm showing you here. Every time your observation and analytical part should be very should be very high to understand the systems if you properly analyze the process. So here I just simply check every day's interval what is the size of the spore and how it is going to increase, and what is the time requirement, what is the environment requirements. So if you see that the from the spore that germination tube is formed, and the germination tube through hypule forms, and then the branch hypule forms, that you can see under the microscope. Up to this you can able to control, and then when it is the mycelium formation takes place, then it's very difficult to control these things. Now here our two things we need to take in care. Everybody optimize the cultivation process, but I have optimized the spore age. Actually, how after how long times I need to keep in the sporic conditions. After that, we can put into the seed cultivations. So and how long time we can able to preserve inside the inside the refrigerating systems, so that after that we can get the better results. So that also one part of the investigation here. And seed cultivations, that definitely every process when you are developing any production process, you have to think about before that seed cultivation, because we are going to minimize the log phases or remove the log phase completely. Seed cultivation is required, so that also need to be optimized. But how do we know that your seed cultivation process is finished? And second one is that how can you optimize a process for the enzyme products? So that part as a whole we studied in the fungal systems. Let us check on the few issue that is definitely is a seed cultivations. When you are going to do, before that we did some experiment on the spore observations. So what we get that basically the spore age, that age of the culture from which the spore is obtained. So that quality of the seed culture depends on the sporage. So what we observe that if you really want a good seed cultivation process, then definitely you have to think about what is the preservation criteria, what is the age of the spore. That definitely create a major rules. We did the experiments at various times interval to understand the physical changes of the spore with different preservation age. That different, and after that we did under microscope. What we observe, basically we observe that after 42 days, then your spore are no more generated, so that basically remain constant. So diameter is very important. You can see here after 42 days, then your that certain amount of spore growth also happens. So that you cannot say that you be keeping in the fridge, then your that your total it is arrested. No, little bit metabolic activity will be there, and after you have to wait up to 42 days also. Even after that, if you go for the cultivation process, then you will get the good results. Now if you go for the seed cultivation process, So if you design for the seed cultivation process, how do I know that your seed cultivation process is about to complete? So here only we did one thing. When we'll get the pH is 6.2, that indicates your fungal seed cultivation process is you can stop the seed cultivation process. That we first we show in the aspergillus. If you look for the secondary metabolites, then seed cultivation you have to end with 6.2. Initially you can start with the 4.5 to that 5 pH. Then it will slightly increase, slowly increase, because they are taking the food and they are growing. And once it comes to the 6.2, you'll see you have to stop it. Either you cannot control in the seed cultivation process, because you can see in the red things, you will see that here that length of the germination tubes in the seed cultivation is slightly increased, and that is 195 that micrometers, that is increased. So up to that is the maximum. If you go more than that, if you wait after 18 hours, then you will face the problems. You are not able to control these fungal systems. So once the seed cultivation is done, then we go for the snaps has been given here, that what is the temperatures, what is the times requirements after various days interval, various hour intervals. So 18 hours, you will see the what is the snap of this of the tubes. So after 3 hours, that germination tubes will be formed, and then a hyphae will be formed. So various times intervals. So what we concluded here, the hyphae alongside of the germination tube was noticed at 28 degrees centigrade, around 196.8 micrometers. But you have to wait up to 18 hours. Initially, when we start the experiment, we have to wait for 1 day, so we can minimize or intensify the process. If you initially wait for 42 days, that means if you are starting the experiments, then after 42 days, then your length of the seed cultivations will be less. Because if you keeping some samples in the freeze or refrigerating conditions, well, you should not worry about the money. But when you are cultivating the systems, you are giving them huge manpower for another 12 hours. You have to spend some money also. So here are the things that seed cultivation process that we have shown you. And after that, we start to optimize the media. We know everybody that nowadays that optimizations, there are lots of tools are there, statistical tools, because one way optimizations is not accepted, because there is a lots of interaction between the two parameters. So we simply keep one parameter change and others are remain constant. So in this way, it's not the mathematically or statistically accepted, or engineering point of view, it is not accepted. Nobody will believe that your system is basically quite rational. It is it does not have any meanings. So people think that there are lots of tools are there nowadays. You can use that response surface methodology, plaque development design, Taguchi methods. So lots of optimization tools are there. But our intention is not here. Our intention is we first need to screen the parameters, because not all parameters are contributed equally for the productions of any products. So we need to first screen, and that's been done by the plaque development designs. Whatever you are expecting, your optimum is where, and your optimum might be in different regions. So here, that COBT approach may not be accepted, and people always do the plaque development design first. The multiple parameter is very huge numbers. Go for the plaque development designs and then screen first. And after screening, you can go for that response surface methodology. There are lots of tools that CCD design you can prefer, or box pattern designs. Or if you think that your parameter is very less and you need a very less number of experiments, then you go for the Taguchi methodology, where your number of experiments will be less. But whatever may be, that statistically it should be significant that what you are doing. So after optimization, so you can go for the designing of the media. But the one beauty of the Taguchi method is that here that signal to noise ratio, it works under signal to noise ratio. That means if you signal even more, if you are getting the good products, good amount of products, but if your error is very high, then it is no more accepted. So here the system works under signal to noise. Now, I already told that that fed batch process is not looks like a batch process. So once you start it, you cannot add. Here you can add any times. So what is your requirement? What is the design part? But you should keep in your mind only one thing: mu should not be greater than the d. D should not be greater than mu. Here we always keep the things that mu is the specific growth rate of the systems. That should be equal to the dilutions of the systems. That should be equal to the dilution of the system. That you need to be taken care. Here on the one part I have just showing here, because fungal, once you start the fungi in the systems, then fungi will start to multiply and a huge multiplication happens. And fungi in the what about the stage I have shown you? No stage can able to produce the enzymes. And you can see that that enzyme initially up to 72 hours there is no enzymes, because that germination tube or in the hyphae or myceli, they are not able to produce any product, secondary product. That's why you need to give the threads. Either you have to cut the fungi myceli in the small pieces, they can produce the beads. Beads, once you give the shock, then what will happen? They will transform the beads. I'm showing you some beads here. You can see the some pictures. So once they will form from that region to that regions, then only they will start to produce the products. So you should to taking care of, basically it is not required for the bacterial system even. It is not required for the algae systems, but the fungi you have to taken care, and that's why people spend more time to concentrate on that area, because designing only the reactor design is not only the part. The process design is also important part, because without proper process design, you even thinking that I'm designing a good reactor, but you are not getting the product because your process is not properly designed. So if you think about that, no, I'm trying to produce the product from that fungi, the myceli, but your product will be very less. So what you have to do? What you have to do? Here you have to do that you have to either increase the agitation speed so that your myceli will be chopped into small pieces and then it will transfer to beads, or you have to increase reduce the pH or increase the pH, whatever may be then the optimum. Here, another things also you can do, that is agitations you can increase, or food limitation that you can do. Here we have done that. So you can see that the substrate concentrations up to 72 hours, we are not adding anything. So your substrate concentration is reduced, so that in that region, your fungi feels that we don't have enough substrate. So we need to convert to the beads. And what they will do, we are giving very minimum amount of food so that up to that level, substrate can be maintained. Initially, substrate was this. Now I'm giving that amount of substrate so that it can be maintained. And it can be maintained another up to 120 hours. Then it will be reduced. Again, we are giving the substrate. So in this way, we are maintaining the substrate at the minimum level. That means fungi always feel that no, there is a threat. We don't have enough funds, so we cannot grow. In the same time, what we did that we are increasing the agitation speed. Initially, agitation speed, once we are increasing that level to that level, so what will happen? In that region, your fungi become chopped into small pieces, and that pieces basically will form the beads, and that process will be continue up to 144 hours. So what we observe here, that is given that your bead, that 7, the initial pH is 7.5 and 7 was considered the optimum for the study. Because if you get the very small number of beads, then your that product will be very high. Because if your bead size is very big, then product formation will not be so much. So small size of the pellets or beads with the high number is expected. Big pellet is not expected. Small pellet is expected, but number should be very high. That we got in the case of the P7 or 7.5. So that is the things. Madam, can I continue or should I stop? Hello? Hello?
Hello, sir.
So,
Yes, sir.
so what is the how much time we have?
1 hour.
So it's next 20 minutes, sir.
Next 20 minutes. Okay. So that's why I'd like to know. Okay. So another process development that we are doing for the bacterial systems. So here I can show you that how we can design a process that required for the secondary metabolites like proteases. You know, that is a most promising drug nowadays for the uh, use for the breast cancer, and we have developed the system here that Serratia martials, that ETC system that basically we have purchased and we have used for the productions of the proteases. With normal way, basically, we usually optimize these systems one way methods, but later on we optimize in the various sophisticated tools we have used for the optimizations of the process. Here we show that that it has a peculiar characteristics. So whatever the color you are getting, that always you will not get. Then we thought that why you are not getting, because bacteria should give the reproducible data. What we observe that when it is in the freezing conditions and once we transfer, we plate it in the we plate, that time it gives the colors. And after that, next day when you are culturing, we are not getting the red colors. So we found would take a long time to understand that we are not giving the proper environment. That's why it is not giving the proper colors. So thing is that once you are streaking on the plates, basically there is a food, the solid fermentation takes place. So until it is food is there, once you transfer the secondary transfer from here to another, they are not in under the thread. They know we have sufficient amount of food. But when it is under freezing conditions, that times a bacteria is under threat. Need environment is not permitting. That in food is not there. So when it cultured in the primary transfer, they will give the colors, but secondary they will not. So here is the thing that need to be maintained, that every times bacteria have to give the use shock. Either they
Hello, sir. Hello, sir.
sorry, sorry, hello, give me allow to
Yes, yes, sir. Yes, sir.
present the slide.
So you are the host.
Madam, extremely sorry because there is some net issue. No, what?
You are the host, sir.
Yes, yes. Okay.
You are the host.
So, if you go for the number of subculturing process, you will see that they are not giving the good yield. So that is the okay. So that if you go for the number of subculturing, what you will see that your product yield is very less. So why it is happening? Once we study that, we study that once you are going to subculturing, that means bacteria is always know that next time I'll also be subculturing enough amount of foods. So that basically you are not under feeling any stress. So that's your product is very less. Next, you are going to optimize the pH. So that is know that everybody 6 to 7. That is for bacteria is good. 7 is good. So 7 usually that production yield is very high. And shocking period. That is one experiment we did. That how long time I'll give the shock. How long time so will just relax there. So here that thing is if you shock for 24 hours, then you will release, then you will get the good result. So that experiments also we did, and although there is no clear-cut mechanisms that why 24 hours is required, maybe from other studies it may be the different. The lot of things are that need to be need to be experimented before giving any conclusion. So here, that is the another part that we tested initially that what type of environment, what type of substrate condition that we have to give so that it can able to produce that good number of the amount of products. So we initially try with the various Newton broth, then LB broth, then peptone glycerol broths. So whatever the result we got, the Newton broth is good, and 30 degrees centigrade is proper for getting the good amount of products. And in case of the nitrate source, what we have tested in the peptone, triptone, ammonium phosphate, ammonium oxalate, ammonium nitrate. But okay, that is peptone is good. Peptone, triptones more or less they're good. For the sugar, if you go for the glucose, fructose, lactose, but lactose is good. That is the one important part we observe that lactose giving the better result than the glucose. Now, that simple optimization we did, we are not going to add here some sophisticated tools. But what we observe that can we use some the powders, sesame powders or peanut powders that we can purchase from the market. Raw materials cost is very less. Can we use that? And if we use, can the productivity increase? So we have tested. Definitely, we got the peanut powders that along with the Newton broth that is good for the getting the at least 31 milligram per liter amount of products you can able to get. And even in the solid media, it gives the clear colors that is required. Now we have went for the cost benefit analysis because after all you have to think about that your product what you are going to produce in the laboratory scale, and then you have developed the technology and you want to transfer this technology to the industrial scale. Then scale up criteria that is very important because whatever you process developed you need to be transferred in the industry. So scale up criteria is that is important, and scale up criteria, after scale up criteria fixing, then you have transferred the system, and then you have to understand what is the cost of the overall process. Now I'm just in between one part I have missed, that is the scale up criteria. Scale up criteria basically done by the 2 to 3 methods. One method is the Reynolds numbers, that impeller Reynolds number. So impeller Reynolds number, that whatever you did in the reactors, that whatever the impeller speed it is, ND square rho by mu, that should be equal for the small reactor and big reactor. So whatever speed you are thinking, he will be 180 rpm or 200 rpm that need to be maintained there to get the submixing. No, it's not like that. It's an equation and you have to put it there and that will be maintained. First one. Second one, I have shown you that TM value, that is mixing taps. So you can fix the mixing taps for both vessels, on the small vessels and bigger vessels. That is that scaled vessel. So that on that basis also you can go for the scale of criteria. Third one is the KLA value, that what I discussed, that is basically the volumetric mass transfer coefficient. On that basis also you can do it. And fourth one, that is very important, that is the power requirements. That means once you start the experiment, you have to spend some power. So on the basis of power requirement also you can go for the scale. After all, you have to, you cannot do the same experiments what you did it here. You cannot do it in the same thing in the industry. So you have to maintain the scale up rules, but taking into consideration that your geometry should be unique. Matlab, what is the meaning of that? Aspect ratio should be equal. So you cannot transfer the conical flash data to the stacked and reactor in the industry. So you have to improve first in the small reactors, small bioreactor, then the pilot bioreactor, then you can go for the industrial scale. So your geometry should be equal. H by D ratio should be equal, aspect ratio. Here, after transferring everything, then you have to think about the cost. Cost is very important, and cost we can segregate in different manner. Here we have segregated, one is cost for the nutrient growth, another is cost for the chemicals, whatever the chemicals you use in the downstream process, and whatever the consumables, chemical.
Hello, sir. Hello, sir. Am I audible? Hello.
Participants, please post the questions. If there is any queries, you can just post the queries in the chat box. Sir will be joining soon.
Madam, I'm extremely sorry, but what can I do? I cannot do anything because it is not by hand. So,
Yes, sir, it's okay, sir.
I will suggest if anyone having any questions that I just let me share one thing, please. I have to forget. Give me allow the guest, please. I hope are you allowing guest? That's why it is a problem.
Sir?
No, no, please allow, please.
Yes, sir.
Mhm.
Yes, sir.
Okay, 5 minutes I will end up. So all the things that all cost you have to take in care, all cost you have to take in care, and then that is for product is 15 milligram we are getting per liter, and here we got the 33 milligrams and we got the 21 milligrams. So if you convert into the per milligram cost, that is 31 rupees, 14 rupees and 23 rupees. As a whole, when we are calculating also the electricity cost for the individual instruments, how long time it is run, and that cost has been calculated based on the reference, and then establishment cost and management cost also we have calculated. Then that warehouse component cost, single batch process, everything we have calculated, and after all, that total depreciation cost also we have calculated. So every instrument having the depreciation values, that 10% we have standard 10% value we have taken in the consideration. Then that all the parameters we are taking into consideration, so media consumable cost, cost of electricity, cost of establishment, warehouse components, so all are taking into consideration. And downstream cost we are taking that 50% around. So packaging and material handling 15% we are taking, and preservation cost, transport cost, all taking into consideration. And after that, we calculated the conventional media. If you go for the 1 milligram producers, it takes to 65 rupees. But if you use the peanut, then rupees is 125, 120. So that is the market price what you are Santa Cruz Biotech what they are selling. So their cost, and we are showing where we stands. So these are the very silent publication that we did in this year, and previous years also we have several publications, and this is our previous students. Now they are doing well. Thank you for your kind patience. Now, if you have any query, you can ask.
Thank you, sir. It's very valuable, everything you have
Thank you.
shared with us, sir. So there are few questions, sir. So how can we use FBR for preparation of value-added products?
Just a minute, please repeat, madam.
So the question from Parameshwari, Miss Parameshwari, how can we use FBR for preparation of value-added products?
Madam, can your students can write these things, because I'm not getting clearly message. Can anyone send this
It's
message,
in chat,
please?
sir. It's in chat box.
Chat box. Okay.
Yes.
So low cost production, secondary material, large scale. How can we use FBR, fluid bed reactor, for preparations of value-added products? So thing is that FBR means you are talking about the fluidized bed reactor. If it is FBR means fluidized bed reactor, then value-added products means we are not talking about the only the microbial products. Value-added products means any products that if it is converted from, let you are looking for the from glucose from cellulose. Here you want to produce the glucose from cellulose. You have the substrate is cellulose. Your product is the glucose. Your enzyme is the cellulase. So cellulase will degrade the cellulose and produce the glucose. So you have to interrupt your cellulose into set the beads. If your beads is, let you are preparing the sodium alginate normal beads, so then your enzyme will be interacted in the beads, and that beads will behave like you can use in the pack bed or fluid edge bed, and you have to send the cellulose in the bottom as a in the lipid media. if the media is passing through the reactor and your bead velocities looks like that your beads are behave like a fluid, then it will be called the fluid HBT reactor. And when the bead is behave like a fluid, then it is a fluid HBT reactor. And during these conditions, your cellulose will be converted to glucose. Then if your product is valuable product is the glucose, in that condition your efficiency will be very high because your whole surface area will participate in the reactions. But if your velocity of the fluid is very less, your bed looks like a packed solid, then your efficiency might less, but the product will form. I hope you get the answer. Anyone? Acha. Which would you suggest as a best reactor to grow spirulina? Now, spirulina is basically the biomass. That basically is a biomass. Now, biomass and product, we are differentiating because product is basically, we consider this product is formed from the biomass or bacteria. Now, spirulina is the cyanobacteria. And basic rule is it depends on the, first you have to evaluate what the parameter is responsible. Here is the problem is the light is the important parameters. Food, carbon dioxide, environment is the important parameters. Now, if your light you give properly and your carbon dioxide level requirement is maintained, then spirulina growth will be done. Now, question is, if you do in the pond, then what happened? Then some bacterial contamination will be done, something will be done. So your whatever the growth will be, you expect the growth found, but the contamination due to the contamination, your cell may be damaged or something may happen. But if you think in the closed system, I can say that design of the reactor is very important so that you can get the 24 means you have to design in such a way that light should go and go into inside the systems, because light penetration is very important. What should be the thickness of the tubular reactors? What should be the thickness of the that will play the major roles. Another question. What would be the sir, what would be the suggest the best reactor for spirulina? I hope it is done. Sir, which reactor is to be used for the plant? Which reactor means I always tell that first you have to understand that your cells behavior. If your cells is not so much robust, then you have to think impeller छोड़ के ऐसा कोई reactor सोचना पड़ेगा. You have to think about the reactor which does not have impeller, like bubble column reactor also you can use. Bubble column reactor is good for the animal cell and plant cell culture, that also you can use. And second one, that which reactor and what is the procedure to be followed any one of the bioactive compound like manganese or unique acid enhancement? That basically you have to know that a metabolic pathway. I'm not working on that, so in that region I cannot give any question. So if it is the reactor design part and if you give some information about the strain, then only I can help you, because these two compounds, one is manganese, that I'm not doing work on that. So what is the metabolic pathway you have to understand first, and second one, what is the compound, what is the strain you are using, that also you have to take in care. What is the behavior of that also you have to take in care. After that, if you give some information, then I can help you which reactor is good. Either is very difficult for me. Second, sir, currently my research work is related to nanoparticles. Can you suggest any upcoming prospective related secondary metabolites in nanotechnology? So you are working on the nanoparticles. So I did not work on the nanoparticles. if you ask me the secondary metabolites, which are very coming future it has used, I can say you that you can go for the, if you go for the enzymes, then that lackage enzymes that you can go for is usually demand. It is basically used for the uh, uh, for lignin separations, and it has a huge impact in the biofuel production. And if you go for the dye, then astaxanthin you can check, or produce is that also a good choice for you. And if you think about the other biomolecules, drugs you are looking for, then I can suggest you think about um, starting groups few drugs. Now it is coming to market that you can look for. Another, currently my research was examined. Okay, can you provide your mail ID, sir, for contacting you and suggestion? Okay, my mail ID is given that. अच्छा, और any question? My currently research to be nanoparticle तो हो गया. Then can you, अच्छा, madam, where should I give my mail ID? Here I can type na. Okay,
Sir,
so
we will
you
give,
can.
sir.
Okay. So, or
Okay,
any
sir.
questions? So some of the fields, thing is that some of the fields I do not know. So I don't have any expertise, so I cannot give the answer. But only if I can help you, if you provide some information regarding the strain and pathway. Thank you. Or any queries, please.
Yes, sir. Thank you, sir. So any
Thank
queries,
you.
any questions from the participants?
Okay.
Tiwari, sir. Sir has joined. Tiwari, sir, good afternoon.
Tiwari sir. Hello.
Okay, sir.
Or any.
Yes, sir. Yes, sir. Thank you, sir. Thank you, Vishwanath, sir, for your valuable time.
Thank you.
And she has
Thank you
shared
very
a
much.
very detailed talk with us. Thank you, sir. Thank you, sir.
Thank you very much.
Thank you all the participants. So it's
Should
really
I?
pleasure to meet you all. So we will meet tomorrow at the same time in the same platform. Thank you to all the organizers.
Madam, hello.
Yes, sir.
Madam, can you please send the recording copy to me? It's possible? No.
Sure, sir. Sure.
Okay. Thank you very much.
Sure, sir.